Delete in doubly linked list. Deletion is the operation of removing an existing node from a doubly linked list. So let us see how can you remove a node from a linked list and do all the associated pointer manipulations so as to keep the linked list in the new form. So coming to deletion, similar to what we discussed in singly linked list case, there are two things that you always have to see. The first thing is before you go to the sub cases of deletion, that is we'll discuss multiple cases, the sub cases of deletion. But before that, before going to all these, you should check whether the list is empty. How do you check if the list is empty? There will be a head pointer. A head pointer, this is supposed to point to the first node in the linked list. So if your head pointer is empty, that is null, if your head pointer is null, that means this linked list do not have any element. And in that case, you can't delete anything. So delete operation should be abandoned if you don't have anything in the list. That is if the list is empty. Second thing is if the list has only one node, that is, let us say there is only one node in this list, then head will be pointing to that node and the next pointer of this node will be null. That is, there is no more node in the list, there is only one node. So you don't have to go to the sub cases of deletion, just check whether the value inside is the one that you want to delete. If it is, just make your head as null. So it is deleted. So these are two cases which you can handle irrespective of the sub cases of deletion. So one is if it is empty. Second is if the list is having only one element. One more thing, whenever you delete an element from a list, we generally what we do is we'll remove it from the list. That is pointer wise, we'll remove the pointer in the list which is pointing to that, which means from the list that particular node will be removed. For example, if I have this node, I removed this. So if my head is null, this node is no more related to the linked list. So the link from the linked list you removed it, but this node is still somewhere in the memory and you have to remove it from the memory using a free operation. So you have to do this if you are handling with a language which do not have automatic garbage collection. Otherwise, it will automatically handle. So generally, it's a good practice that whenever you remove something from a linked list, make sure that you free it manually because that's a good practice. Okay. So let us start. There are three subcases of deletion. First thing is when you're deleting from the beginning. Second case is when you're deleting from the end of the list. And third case if you're deleting from a specific position in the list. So we have to see for all these subcases and how to do delete in a doubly linked list in these cases. Let us start with deletion in the beginning. First case is deletion in the beginning. Let us say this is your linked list. 1, 2, 3. You have 3 nodes. You have a head pointer. This head pointer is supposed to point to the first node. Each node will have a next pointer, will point to the next node, and a previous pointer which will point to the previous node. Let us say the values are 15, 9, and 41. These are the values. I want to delete from beginning. That is this node which is having value 15. This is to be deleted. What is to be done? Simple operation is to update the head to point to the next node. So even in singly linked list, what did we do? We updated this head pointer to point to the next node. So my head is now pointing to 19. My head is pointing to 9. So my head is pointing to 9 means presently the first node in my list is 9, which means 15 is out of the list. It is irrelevant. In singly linked list, simply when you change the head to 9, the work was done. But because this is a doubly linked list, there is one more additional work, that is to manipulate the previous pointer of the node with value 9. That is whatever was your second node previously, that node's previous pointer should be made null. Why should it be made null? Consider this is not here. Still, your linked list first node, presently your first node is 9 because you changed your head to point to the second node. This will have a previous pointer. This is pointing to the node which was previously the first node, which you deleted. So what do you have to do? You have to make the previous pointer of the new head as null. So there are two steps. First step is to make head point to the second node, and second step is to make its previous pointer as null. This previous pointer which was existing, that you have to make as the null. So once this is done, your deletion of the first node in a doubly linked list is done. And an additional thing is to free whatever was here. So you use your good judgment to free it. And what is the time and space complexity? Time complexity is order of 1. It is a constant operation. You just made head point to the next node. And what is the space complexity? You didn't use any extra space. So space complexity is order of 1. So this is about the deletion at the beginning. Next case is deletion at end. And one more thing, in deletion at beginning case, doubly linked list do not bring any advantage. In fact, it brings in a disadvantage that you have to manipulate the previous pointer as well. Okay, let us go to the case of deletion at the end. If you want to delete at end, I'm restoring this here, 15 having next pointer here, 9 is having a previous pointer, my head is pointing to 15. Okay, this time I want to remove the last node, that is with value 41. So what are the steps? The first thing you have to do is to reach this particular node. So same as the case of singly linked list, start traversing from the head and traverse till you reach the node just before the node you want to delete. That is, go till the second last node. Once you reach the second last node, stop there and do the same operation as you did in case of singly linked list. That is, remove the next pointer which was pointing to the last node. So make the next pointer of the second last node to null. So this is the first thing you have to do. Next thing is to update the previous point. So the previous pointer you need not update in this case because this is out of the list now. So this previous pointer doesn't have any significance. It is not going to do anything. Anyway, you are going to remove this from the memory. So in this case, deletion case, only two steps are there. One is traverse till the second last node, that is deletion at the end. Okay, I'm considering deletion at the end of the list. That is, you want to delete the last node. Traverse till the second last node starting from the head. Once you reach the second last node, just make the next pointer of second last node, whichever was the, make it null. That is, remove that pointer. If this is done, your deletion from the end process is done and this is now taken off. Okay, this you are freeing from memory. So what is the time complexity? Time complexity is order of n. Why is it order of n? Because you have to traverse till the second last node. So that means you have to go through n minus 1 nodes, which is order of n. And what is the space complexity? Order of 1, because you're not using any extra space. There is a special case here to consider. And this special case is important because this is something which makes a double linked list special over singly linked list. Okay. So let us say my 41 is here. I want to remove this last node. This is a special case that I am maintaining a tail pointer as well. That is, in linked list you can maintain an optional tail pointer which will point to the last node in the list. In case of singly linked list, we are told that even if you have a tail pointer, deletion from the end will still take order of n time. Why was it? Because even if you have a tail pointer, to delete it, you have to reach the node just before the last. You have to reach the second last node. And in a singly linked list, even if you have a tail pointer, you can't reach second last node. You can only reach the last node. If you want to reach second last node, you have to traverse from beginning and reach till there. But because this is a doubly linked list, you have a previous pointer using which from the tail you can reach the second last node. Because of that, if you are maintaining a tail pointer in a doubly linked list, removal from end will become order of 1. So this is one area where doubly linked list will get an advantage over singly linked list. So it will be order of 1 space, order of 1 time operation if you are maintaining a tail pointer. Okay, that is the condition for deletion from the end. The next case is a deletion at a specific position. Let us see that case as well. And let us see whether doubly linked list is having some advantage over the singly linked list or not. Okay, you are going to delete from some specific position. Okay, this is the third case. Third case is deletion from a specific position. So I'm having the same linked list 15, 9 and 41. These are my nodes. I'm restoring my pointers, next pointer and previous pointer, and I'm having a head pointer which is pointing to first node. Okay. What do I have to do? I have to delete from some specific position. So let us say I want to delete from here. Let us say I'm saying index 2 I want to delete, or index 3 I want to delete, whatever. So let us say index 2 I want to delete. What is the first step? Same as singly linked list. You have to start traversing from head reach till the node that you want to delete. But should you go till the node you want to delete? No, you should generally go one node beforehand, right? You have to stop there. But because this is a doubly linked list, you have an advantage that you have a previous pointer as well. You have a pointer which is pointing to the previous node. And because of that, you need not stop at the previous node. Instead, you can go till the node that you want to delete. Okay. Let us say you reached here. If it is singly linked list, you have to stop before and do this. In doubly linked list, it's better you come here and do. Wherever you may be, you can still do. Okay. You can do from the node before this as well, but this will be probably easier to understand and easier to implement. Okay. Let's say you reached here. You want to remove this node only. Okay. So what are the steps? So first thing is to update the next pointer of the preceding node to point to the node after the target node. Why should you do this? See, coming to linked list, the order of operations is very crucial, because if you don't follow the correct order, you may lose some link and you may not be able to complete operation. That we had explained in previous lecture also, that if you don't follow the right order of operations, you won't be able to maintain the complete links to the list. You may miss some link and you may not be able to connect to the next node at all. So when you are deleting, let's say you reach this position, first thing you have to do is to make the next pointer of the previous node point to the succeeding node. So how do you do this? You want to, now you have a new pointer. Let us say this pointer is presently pointing to this node because you reached here. This was your traversal pointer. You reach this point. You know you want to delete 9. What would you do? You go to 15. That is, you see whatever is the next pointer of 15. You make that next pointer point to the succeeding node. Succeeding node means succeeding node of 9. So make 15 point to 41. With this operation, what did you do? You made sure that link is not broken. The link in this list is not broken, because now even if you break something in 9, even if you break all links with 9, still you have a way of reaching from 15 to 41. So you made sure that the linked list is still there even if you remove the element 9. Okay. So you did the first step, that is updating the next pointer of the preceding node, next pointer of the preceding node to the succeeding node. So when I say preceding and succeeding, it's the preceding and succeeding of the node you want to delete. Okay. Next step is to update the previous pointer of the succeeding node to point to the node before the target node. That is, you want to update the previous pointer of the succeeding node and make it point to the node before the target node. So now you established the link, next and previous pointers link in this linked list. Now you are safe to remove the links that are related to 9. So now you can remove this next pointer, you can remove this previous pointer. You need not remove actually, because you are anyway going to free this. So you need not remove the pointer. Once you updated the pointers, next pointer of 15 and previous pointer of 41, you are good to go. You can, that means 9 is no more relevant, because when you are reaching from head, you will reach 15. So you have no way of reaching 9 now, because 15's next pointer is pointing to 41. 41's previous pointer is pointing to 15. So even if 9 has a next pointer to 41 and a previous pointer to 15, there is no way of reaching 9. 9 is now out of this list. Okay. Then you can just free this 9 so that 9 goes out of memory. If you are using a language with automatic garbage collection, it will be automatically removed. Okay. And whenever you are searching for some specific position, if this position is not found, that is a special case, you can't delete. Here we are considering that you are able to find the position. Okay. So this is how you update in a doubly linked list in order to delete from a specific position. And what is the time and space complexity here? Time complexity is order of n. Why order of n? For traversing till the point you want to delete. Okay. And space is order of 1, because for deletion you are not using any extra space. There is a there are two special cases here. One is if you want to delete a node with some particular value, then you have to use the search algorithm. You have to search in the doubly linked list, find out that node. After that, it's the same. You just have to delete as we discussed right now. If it is index based, then you have to reach till that index and do this. Is there any advantage over singly linked list? That is the question. Yes, it is, and it is in another special case. Let us say this 9 is still there. Okay, 9 is still there, and these links are also intact. And instead of the way I told you till now, that is, instead of saying that I want to delete index 2 or that I have to delete index node with value 9, instead, if I am directly giving you a pointer which will point to the node I want to delete. In this case, doubly linked list can handle this in order of 1 time, while singly linked list will still take order of n time. This is the only case. This is not the only case, because in deletion at the end also we had discussed that in doubly linked list you have an advantage over singly linked list in a special case. So here, if I am giving a pointer which will directly point to the node I want to delete, in that case, in doubly linked list, I can do it in order of 1 time, because if I know the pointer to this, I can, what should I do? I should make the previous pointer of the next pointer of the preceding node point to the succeeding node, and I should make the previous pointer of the succeeding node point to the preceding node. I can do this if I have a pointer to 9, okay, because it is a doubly linked list. But if it is a singly linked list, I can't do this, because I from this I can't go to the preceding node. That option is not there in singly linked list. So singly linked list, even if I give a direct pointer to the node I want to delete, it will still take order of n. But because this is a doubly linked list, if I'm giving a direct pointer to the node I want to delete, I can delete it in order of 1 time. So this is one case where doubly linked list gets an advantage over singly linked list.